Well, hello class. Welcome to AP Chemistry and welcome to today's Periodic Trends lecture. Okay, so anyways, I hope you had an excellent weekend and I hope today is just as good. So we'll probably do some notes, probably talk with our partners, probably do some cool stuff with trends. And let me be honest with you, trends isn't the worst stuff that we cover. Okay, so this stuff isn't too bad. So anyways, all right, so the periodic table is kind of set up and it's set up in such a way where you can unlock super cool mysteries with it. And so it's our roadmap to understanding atomic structure and properties and everything. So basically, we're going to look at trends and patterns based upon atomic structure. So a trend is just a pattern. You know, if someone says, "Oh, you're so trendy," they're saying, "Oh, wow, look, your clothes are so nice and everybody likes that kind of stuff." So a trend is just basically a pattern. So we're going to explore trends and patterns found on the periodic table. Okay, here goes. All right, so the first thing we're kind of talk about is effective nuclear charge with the abbreviation ZF, ZEF. Okay, so because electrons are negative, right, and they're attracted to the nucleus, remember Coulomb's law is opposites, you know, charges attract and the distance, all that kind of stuff. So how attracted they are is going to be based upon a couple factors. The basically electron configuration, that 1s2 business, and then also like how strong is the nucleus at pulling those electrons in. And so those are some of the factors. So in this case, Z is going to be the atomic number, and S here is going to be the core electrons. We kind of already talked about core electrons, but you know, the core electrons is how many are not valence, basically. So you're going to ask you a question like, which one has greater effective nuclear charge, neon or phosphorus, and why? Okay, so if we take a look at this, we can see that neon, if you look on this periodic table, has 10 electrons and then 10 neutrons, and it kind of looks like this. Let's look at the electron configuration. 1s2, 2s2, 2p6. That's neon, right? And then these are the core, and these are the valence right here. And then we have phosphorus, which looks like this: 1s2, 2s2, 2p6. Whoa, that's a 6. 3s2, 3p3, I believe. I think it has 15. Yep. So these are your core. So if we're looking at an effective nuclear charge, we're going to take a look at basically your atomic number, which in this case would be 10, minus how many core electrons, so 2. So this would have a ZEF of 8 versus this one. Take a look at this one. So over here, we have, so it looks like the atomic number is 15, so that's Z, minus core electrons is 10. So we have 5 here. So which electrons would be pulled closer to the nucleus? We would say this one because it has a higher effective nuclear charge. Okay, so basically, if you have more protons in the nucleus and less core electrons, they're going to drag them closer through attraction, through Coulomb's law, because remember, distance and charge are the two factors that draw these electrons in. So there's a little trend too, a pattern on this table up here. So see the table? So as you go across the table, so actually if we're going across, it should be going from lithium to fluorine, the nuclear charge increases, everybody. So the nuclear charge increases. And so that's kind of like a trend or a pattern. Basically, the nucleus becomes better at sucking in electrons because you're adding protons each way through. I don't know why I'm taking care of that. Okay, so let's keep going. So this is good stuff. So effective nuclear charge is basically looking at how effective is the nucleus at drawing electrons in, and a couple factors: the inner core electrons, and then like how much, you know, how many protons are in the nucleus. Okay, this is so much fun. Okay, now when working with trends, there's going to be like 4 explanations, and the way trends usually appear on the AP test is you're usually going to have to, like, you know, describe something and then explain it or justify your answer using trends or patterns based on the atomic structure. So So we already have our rule, if you don't know what to do in chemistry, find moles, and that's a good rule. So totally a good rule. Like if it's a calculation, do that. If it's a structure question, or something about atomic structure or patterns, the rule is when in doubt, draw it out. Okay, so when in doubt, draw it out. Like draw out the electron configuration. Why is this one work better than this one? Draw it out. Like think about structure and then understand its structure and then explain it. Okay, so there are 4 factors that affect the patterns on the periodic table. Trends is just as patterns on the periodic table. They're going to be nuclear charge, which we just talked about. It's how good is that nucleus at drawing in electrons. If that nucleus has lots and lots of protons in it and the electrons are really, really close to it, they're going to really, really be drawn in, and that would cause it to have certain properties. Okay, so nuclear charge represents the charge on the nucleus. So that's something that will be one of the factors on it. Then other factor is going to be shielding. Okay, so usually in class I would talk about this, but you guys eventually will be going to concerts and stuff, and that's kind of a fun thing about being young. And I went to random concerts back in my day. I went to Pink Floyd, that was cool, and Stone Temple Pilots, and all sorts of cool concerts. And there's always that guy that's there, and he's like 10 feet tall, and he's ginormous. And then here's you, right? Now, actually, usually I'm that guy, and here's the band. Okay, so over here. So like you're trying to watch, but they have they're ginormous. You can't see around them. So it happens at sports games too. I was just using concerts as an example. So they kind of block your view. So it's interesting, right? So you can actually be shielded. So now let's look at it in terms of electrons. So you have the nucleus, which is positive, right? And you have a bunch of shells here. And then you have this little tiny electron way out on the outside, a valence electron. And it's like, oh, I want to see how close. It can't because it's shielded. It's blocked. And that's what shielding is the inner electrons block the electrons. And what happens is shield electrons are really easy to lose because there's very little attraction, because the nucleus is not very effective at attracting because it's shielded. Okay, so this is how we describe or answer things. Okay, similarly, it's hard to get that word out. Likewise, atomic radius is kind of like along the same lines as shielded, but if the distance is greater, there's also less attraction. So you could use that in a lot of times. And then we kind of hinted on this the other day, but sublevel. So like having full or partially full sublevels it requires extra energy when you're trying to lose electrons if it's already full. So these are the main factors when we say, why did this do the things it do? So when we explain the trends, you have to use these things. Use nuclear charge. Usually it's this one is a lot and this one is a lot. These ones are sometimes. And we're going to look at specifics, and we'll look at AP type questions and go from there. Okay, so the very first trend is the trend in atomic size or atomic radii. So you might see it as atomic radii, which is just a fancy word for size. Okay, so we're going to talk trends in terms of period trends and group trends. So you remember from the very first unit that period represents horizontal trends. So you're going to look for a trend across the table, and then you're going to look at trend up and down, and you have to be able to justify it or explain it. Now, note to self, don't use because the trend said so in your justification. You have to justify it based on atomic structure. So the first trend is the trend in atomic radii. It tends to decrease as you go across the period. Now, if you look, there are always some exceptions to this. If you were to look up the actual values, and you don't actually have to look at the values, you just have to be able to explain why one thing is the other. And remember, when in doubt, draw it out. So you're going to kind of draw out the structures, figure things out, look at atomic nuclear charge, all that. So basically, as you go across the period, they get smaller. So if you look on the period, so period 2, which would be the second row, so you have BE versus B, okay, in the epic matchup. So BE is right here and B is right here. We would say that BE is larger, even though it only has 2 electrons, even though it only has 2 protons, than B, which is actually smaller. And you can kind of tell from the picture too. So size decreases as you go across the period. Now, as you go down a group, okay, so as you're going down a group, if we were comparing B versus AL, so if you can take a look at the periodic table, C and group 13, there's B and AL, This one is bigger because as you go down a group or a family, that's what we call them, they tend to increase in size. Okay, so why? Why did they get bigger as you go down and get smaller as you go across? And so a lot of people, you can't say they get bigger because the arrow says, going down it gets bigger. 0 points. Okay. So what causes it to get bigger is these things. Okay. So atomic size increases down a group because, the electrons are further from the nucleus. There's more shielding. And every single time that you go down the group, you're adding a layer. Think of like stoppers, or you can think of this scene from Shrek. Do you remember this scene from Shrek? Okay. He's like, ogres have layers. Okay. That's a horrible Scottish accent, but he's talking about it and Donkey's like, he's calling them parfait, but he's like, they're onions. All right, whatever. So think of it this way, right? The atom is bigger as you go down. Oh. Okay, so here's one layer, and then you're adding. See, every time I add an energy level, it gets bigger, doesn't it? That's what happens when you go down a group. Okay, you're adding energy levels, and that's why it gets bigger. There's more shielding. Everything happens as you go down a group, and then as you go across, it gets smaller because every time you add a proton to the nucleus gets stronger. Okay, and since it's stronger, what actually happens is I always like to see attraction leads to contraction, right? So if this gets really, really strong and you're a negative electron, and this is getting stronger and stronger, what happens is it draws it in closer and closer. And since it's closer and closer, it actually shrinks. So the greater the nuclear charge, the smaller the atom. So going down, we would say they increase because of there's more energy levels, there's more shielding. Going across, we would say there's more nuclear charge. That's why they get smaller. All right, so here we go. Look at this. This is so much fun. Okay, what's bigger? Okay, Li or F? Okay, so Li is on that side over there. Okay, and F is over here. So you can see that size decreases as you go across. So greater size would be this one right here, which is weird too, right? Only has 3 protons, but if you were to look at it, it is bigger than the other one. All right, Mg or Ca. So in the same group, they're in group 2, but Ca is further down, so it'd be that one. And we would say it has more energy levels or shells, which causes more shielding, which causes it to be larger. Okay, molybdenum or antimony. So molybdenum is further to the left. Antimony is right there. So since this one is further to the left, this would be stronger because, again, this one tends to have more nuclear charge, which draws it in. And then selenium or sulfur, you can see selenium is further down, so it's this one. So being able to understand what's strong, relative size and explain it, that's a big deal in trends. Remember, when in doubt, draw it out. Okay, let's keep going. This is great. We talked about ogres having layers. Just think of that. Think of that epic scene. In class, I might even put that scene on. It is on YouTube. Hopefully you saw Shrek. Okay, now you're going to find that they also have a trend in ionic size. Okay, so ionic size is, okay, you remember how sodium can become Na+, and we call positive ions. So these would be positive ions. These are called cations. So cations, let me move this out of the way a little bit. Cations are always smaller than the parent atom because removing an electron decreases electron-electron repulsion, so the electron cloud contracts. So picture it this way. So cations are smaller than their parents, okay? So first of all, are you smaller than your parent? Are you shorter than your mom or dad? I'm actually taller than I'm more like an anion, and we'll talk about that next. But so it's interesting to think about like where we get our heights and all that. But for cations, they're smaller than the parent. So let me explain what that is. So Na is the parent, and Na plus would be the cation. So this is like the before, and this is the after. So we call this the parent. And what happens is, so this one has 11 protons, and this one also has 11 protons, but this one has 11 electrons. This one only has 10. So since the nucleus has got more nuclear charge than the electrons, and there's less electron-electron repulsion, what happens is that attraction leads to contraction. It's like and shrinks. And so cations are always smaller than their parents. Now, the opposite is true for anions. So if we have F, and this would be the parent, and then F minus would be the ion, the A negative ion. And what happens is this one has more electrons than protons. And so since there's more negative charges, they're like, ugh, negative charges, oh, I hate you. So they expand and you get a bigger size. So the trend goes the same way if you look at this, okay? So the trend's the same. So as you go across the period, even for anions and cations, they get smaller in size as you go across. So going this way, they get smaller. And then going down, they also increase for the same reason. You know, as you go down, they still have more shells, and that still causes them to get bigger. So trends in ionic size, if they're talking about ionic radius or ionic size, it's the same thing. So oftentimes I'll just write, okay, so the trend going to the right decreases, increases. And if you know this, you kind of know them all because it's the same trend and you can just kind of follow the patterns. Okay, so let's do this. Which is smaller, SR or MG? And so here's SR right here, and here's MG. And so the smaller one would be MG because it's further up on the chart. Now, that's not a good explanation. We could say that SR has more sub-levels and energy levels full, and there's more shielding and all those factors that cause it to be bigger, okay? And then when we compare P, so here's P and here's S, okay, so those two, you can see that size decreases as you go to the right. So we would say that S is smaller, okay? And since S is smaller, you would say, well, you know, there's more. Actually, it's the same reason. Like as you go across, the nucleus gets stronger and stronger. And if you look at this, so we have P -3 and S -2 are the two ions we're comparing, because on the chart, that's what the ions they typically compare. Do you see how this has more electrons? And since it has more electrons, there's more electron-electron repulsion. There's less attraction, and so that's why it's bigger, and this one would be smaller. Okay, and finally, if we look, lastly, let me erase this real quick. We have BR or C, and so you have BR and you have C. And look, this isn't comparing at anything. So usually they're going to be right next to each other. But if you had to guess, what would you guess? Is it C? Is it BR? It depends on what type of ion it forms. You know, if C is +4, that's a whole different story. So in this one, I'd probably look up a chart and find out which is which. But they're not going to give you that. They don't do that. Okay, now this is very, very common. So arrange these in order of an increasing atomic size. So I like to do is this, is I like to put an S, so that's small to large, right? Small to large. And so I look at my chart and I find out we have S and GE and P and SI. So S, GE, P. Okay, so my biggest is going to be GE because it's furthest down and furthest to the left. Okay, and then over next, the smallest one would be S. Okay, so S would be the smallest, followed by P, and then followed by SI. Okay, so this would be something that you do, and you just kind of use the arrows to figure it out. Okay, now this one's cool. So this is isoelectronic. We learned that isoelectronic means that they have the same atomic structure, you know, same electrons, everything's the same. So in this case, these are all isoelectronic with neon. Okay, now in terms of structure, do you see how this has the most electrons? This one has 10 electrons, but only 8 protons, because the atomic number for oxygen is 8, and it has 10 electrons because it's isoelectronic with neon. So if that's the case, look, those eight positive protons can barely hold in those 10 electrons. So this one's big. And then look at this one. This one has 12 positive protons to the 10 negative electrons. So this has got way more nuclear charge. So what happens is that one's the smallest. Remember, cations are smaller than their parents. Anions are larger than the parents. So look for the most positive ions when you're trying to explain these. Wow, this is so good. Okay. So trends in ionization energy. All right, so ionization energy is the energy to remove one electron, this one. Okay, and this is exactly opposite of the trend for size. So let me give you an example of ionization energy. So let's say we're sitting here with lithium. Lithium, we have 1 valence electron, or we could say, let's say we have iodine with 53 electrons in it, but only 7 valence. That's an important step to remember how many valence it has. Okay, so which would be easier to remove an electron? Would it be easier to remove an electron from Li or from I? Well, it's way easier from Li because Li, lithium, only has one valence. So it's not very hard to remove electrons when you only have 1 or 2 valence electrons. When you have 7, it's kind of tricky. Okay, so ionization energy is the energy needed to remove an electron. So you have to overcome the nucleus and pluck it off. Okay, so as you go across the period, it increases. And as you go down a group, it decreases. All right, so we're going to talk about why here. So, and understanding that. Well, I went too far. So why does it increase as you go down a group or decrease as you go down a group? Well, as you go down a group, there's more and more shielding. So it's really easy to remove electron as they get bigger. And we'll learn this when we do our lab and everything, but it's super easy because there's very little traction. Remember, Coulomb's law looks at distance and attraction. And since they're further away, there's less attraction, and you can just pluck them off. Electrons just come off easy. And then as you go across, they get smaller. And as they're smaller, it's harder or more difficult to remove electrons. So there's that. Okay, so when we write this, so to properly write the ionization energy, it looks like this. So you're going to have something like sodium, and it's always in its gaseous state, to become an Na plus ion or a cation, and then plus an electron. So it's going to look like that. That is the general format for it. Okay, now this sometimes you remove 1 electron, but like if you have Mg, right, you actually can remove 2 electrons. And so to the first ionization energy, is the energy needed to remove 1 electron. The second ionization energy is the energy to remove the second electron. So once you reach the core, there's a huge jump. Okay, so let's say I can remove 1 electron from magnesium, I can remove 2, but when I try to move 3, there's like a giant peak. And so something like this is what you'll look at here. So we'll show you an example of that at some point. So if I was to arrange these in the increasing ionization energy, remember the trend goes like this. So as I go down a table, it decreases. And as I go this way, it increases. So you just have to arrange them properly. And so in this case, so I'm raising and increasing. So I like to do it like this, from small to large. That way I don't mess up the order, because sometimes people do it exactly backwards. And so let's see, I guess I have to look at it. So BeCa, this is awkward, N and P. Okay, so we know that N is going to have a really, really high one because it's furthest to the right and highest up. And then of these two, BE is going to be, and then Ca is going to have the lowest. So gabetin is the answer, but gabetin. So calcium would have the smallest ionization energy, followed by beryllium, followed by phosphorus, followed by nitrogen. And then we've kind of been working on this, but does everybody see that this one shouldn't exist? Because once you get in the core, they just tend not to. Like K plus makes sense. K2 plus doesn't. I mean, it's possible, but you'd have to overcome a lot of energy for it to occur. All right, so look at this one. So what period is this one from? So you have 3 ionization energies. So this represents the first, the second, the third, and then boom, the fourth. So here's what happens here is you hit the core. Okay, so what this is saying is that it's low, 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 relatively low, high. And so you have 3 valence electrons is what this is saying. So this would be aluminum. Now magnesium has 2 valence electrons. So what you would expect with magnesium is it would be low, low, high, right? At some point, and sodium has 1, so it'd be low, high. So what happens is there's a big jump in ionization energy once you hit a core electron, because it's hard to overcome the attraction of the nucleus once you hit core. All right, the last trend is affinity. And affinity is just that, it's love. All right, so these things tend to have love for electrons. We'll be talking about this in terms of electronegativity and affinity, but it also is the same trend as ionization energy. So the love for electrons, affinity here, increases as you go across the table and then decreases as you go down a group. So in this group, the highest affinity would be chlorine, if you take a look at the trends. And we'll probably do some more work with this and work with our partners. I'm running a little bit long on this video, so I want to kind of end it, but trends are cool, right? If you can draw it out, you understand the structure, you can justify it. we want lots of trends questions on our AP tests. Okay, we're going to call it quits, people. I hope this video was good. I was in a little bit of a mood, as you can tell. So let's finish.